well, thank you. Thanks for the organizers for the invitation, the possibility to speak here. Thanks for everyone for coming. So I'm indeed talking about the localization of particles in quantum field theory. And to start this off, the consensus view definitely is that in philosophy of physics that quantum field theory is not about particles, at least at the fundamental level. And here's a few assorted quotes to show that. I'll just read the most pointed one by Redhead. Particle states are an idealization which leads to a plethora of misunderstandings about what is going on in quantum field theory. The theory is about fields and their local excitations. That is all there is to it. So if quantum field theory is not about particles, what is this? If you generally worry what this is, on the left side that is a picture of a bubble chamber where we can see tracks of particles that are charged, and on the right side we see the depiction of one of the collision events at CERN, where we also can see that we are looking at particle tracks. So somehow we need to bridge this gap between the theory explicitly not allowing for a particle ontology and apparent particle phenomenology. So our goal is we want something that models localized states, at least in some sense, that can also model multi-particle states, so states with multiple localizations. And ideally we'll also have something that explains how these particles, which are usually only considered in the free case, emerge from interacting theories. I'll not be discussing the third point too much today. That's sort of more of an outlook thing at the end. But I hope I'll convince you of the project before that anyways. Okay, so the plan is I'll just, before getting actually to the content, some basic setting annotations. Then I'll introduce the no-go theorems that sort of tell us that we cannot have localization in quantum field theories. Most importantly, I'll be talking about the Schlieder theorem, and then I'll present two responses that can be seen to responding to different aspects of the consequences of the Schlieder theorem. I'll compare those approaches, and we will see that there emerges a nice generalization of that. And we'll then look at how this notion of localization can lead to the definition of particle states. And as I said, in the end, we'll talk a bit about how that meshes with interactions. Okay. I'm considering a quantum field theory on Minkowski space-time. Most of what I say will hold in more general space-times, but to be on the safe side, will just be in R4. And there's basically two ways how to set up a quantum field theory. In that setting, we can either look at the field operators that act on some Hilbert space. I'll, for lack of a better name, call that the field-first approach. Or we might associate operator algebras to regions of space-time. That's the algebraic approach, together with sort of the collection of all operators across space-time, which is the, sometimes called the quasi-local algebra. We also need the implementation of space-time translations. In general, we'll want all space-time symmetries, but we explicitly will only be using translations here. And most importantly, on the algebra, I'll denote those by this alpha sub x automorphism. Well, states are then given by vectors or linear functionals on the algebras. And in particular, the vacuum vector I'll denote by ket omega or by the small omega 0. Because in the algebraic case, all the states will somehow be called omega. Yeah, I'm only considering bosonic field theories, so we'll only see commutators, no anti-commutators. most of what I say generalizes to fermionic theories, but as usual, there's complications. How are particles usually constructed, or like basically constructed in quantum field theories? Well, usually we start with a free theory and we try to define a one-particle Hilbert space. We can do that with the Wigner-style analysis. There's other possibilities, but sort of that's a very nice one, where we look at representations of the space-time symmetry group, and those representations give us the one-particle Hilbert spaces. From that, we then construct the full Hilbert space of the theory, which is the direct sum of the n-fold products of the one-particle Hilbert spaces. So the n-fold products are sort of n-particle states, and the direct sum over all of them is our whole Fock space. And if we do that, we can usually choose a basis that we can label the states in the Fock space by the momenta of the particles it contains. All right, so much for the basics. No-go theorems. So these tell us why we can't have localized systems in quantum field theory, even compared to how sort of we have unsharp positions in non-relativistic quantum mechanics anyways. So in non-relativistic quantum mechanics, we can set up a system of projection operators that implement the propositions of my system is localized in this region. And the purpose of the no-go theorem, or what the no-go theorems then show us, that this is not possible in relativistic theories. We can't have systems of projection operators implementing those propositions if we assume some usually naturally motivated things about them. Sometimes this is put as a reason for why we go over to quantum field theory. Don't want to talk too much on that point, but sort of one can view this shift to quantum field theory as a response to that, because we attach the operators themselves to regions in space-time instead of trying to come up with a system of propositions. So if we have a field operator, we would say this is localized around X. If we have an algebra of observables for an open region in space-time, we say that these are the observables in that region of space-time. And the idea then is those represent somehow the local properties of the system. However, the Ray-Schlieder theorem also does constrain that a bit. And so here's the statement, which says that if we take any open region of space-time, be it as small as we want, as long as it's open, and non-empty, then all the local operators associated to that region, if we take all these operators and act with them on the vacuum state, we can actually approximate any arbitrary state of the theory. So by choosing operators in this very region, I can approximate something where, I don't know, there's an orchestra playing on some star somewhere. That's a bit weird, and that sort of somehow constrains the notion of how local these operators are. But nevertheless, the way I want to look at the theorem is through this corollary. Namely, if I take an operator, it cannot be both being strictly local and annihilating the vacuum. This is because from the Ray-Schlieder theorem, we can conclude that any state of finite energy, in particular the vacuum, is what is called separating. So the value of any operator on that state fixes the operator. So if that were zero for the vacuum, we'd have to conclude, if C is also strictly local, that C has to be zero. So we have to choose one of those to give it up, and that's sort of how I want to frame the approaches to localization. Why these things? Well, we would want from an observable that describes properties of particles that they're zero in the vacuum, because there should be particles in the vacuum, and that they are describing local excitations or local properties of a particle being somewhere. So this is exactly what we want. Obviously, we also want them to be non-trivial. So how can we characterize a state as being localized in a bounded region without running into these consequences? And I will frame the two proposals as two responses. We can give up the requirement that we want the operators to be zero in the vacuum and just say, well, there's vacuum fluctuations, whatever. Then we get what I claim, we get what Wallace proposed, namely effective localization. We could also give up strict locality, which happens in the literature on Haag scattering theory, and from which I will extract and propose this notion of almost localization. Or we give up non-trivialism and end up with nihilism or something like that. So we don't want that. Okay. So Wallace proposes that we call a state effectively localized at some time t in a region if and only if the difference of the expectation values on that state for operators made out of the field operators in that region is very different to the vacuum expectation values in that region. And as soon as we take field operators from outside of that region, the difference of expectation values drops off. So outside of the region, the state looks like the vacuum. And Wallace then goes on to show that using some known quantization procedures, how we get to the Fock space, we can actually construct such states if we start with reasonably localized classical fields. All right, the other approach is based on a notion proposed by Haag, which is almost local operators. And the idea is that we relax the strict locality requirement for the operators. So we call an operator that's not strictly local, almost local, if basically it can be approximated by local operators to an arbitrary degree. In particular, we want that there is a family of growing double cones, concentric double cones in space-time growing in radius, and strictly local operators from those growing double cones, so that they approximate the almost local operator with a rate that is faster than any polynomial. So again, we have this super polynomial approximation, which will become very relevant. I'll have a picture very soon to get a bit of a better intuition on that. So it says here that the double cones are around the origin, so around the 0 point. We will just use the space-time translations to shift our operator to wherever we want it. And finally, because we can have strictly local operators that approximate our almost local operator to any given degree, for any given error bound, we can sort of have the smallest r, the smallest radius of this double cone, so that there is a strictly local operator in that region that approximates our almost local operator better than the given error bound that we had. So we might want to imagine something like this. The A is the almost local operator and sort of has support everywhere in space-time, but we have these concentric double cones, and the contribution of the strictly local operators from within there drop off fast the larger R gets. And then we shift that around in space-time, and have an almost local operator around some point x. Why do we do that? Well, because they're not strictly local operators, they can be vacuum annihilating. So we can require those operators to be zero in the vacuum. And because we were really careful with the limiting behaviors, we can actually prove theorems that show that those almost local operators almost behave like actual local operators. So for example, here we have asymptotic abelianness for those operators. So if we take two almost local operators, shift them far apart in space-time, then they will commute. Okay, how can we use that to characterize a state as almost localized? Well, first we choose what Haag and others call the algebra of detectors. So we designate a set of observables as detector observables, and we choose almost local operators that are positive and annihilate the vacuum. And then what we do is we test the state in different space-time points with almost local operators localized around different space-time points. So we call a state almost localized in some spatial region O if for any almost local operator that we could choose, positive and a vacuum annihilating, the farther we go away from O, the smaller the expectation value we'll get. We again will have super polynomial drop-off. Again, a little picture, so assume that this is sort of the region O, where we want the state to be localized, and then we just test it with some local operators, and they might be outside of O, or inside, or at the boundary, which shows us why we sort of can't say, oh, there shall be zero outside of O, and only have positive values inside of O. Because not only will those operators have support, if ever so small, everywhere, and also those placements might mess that up. But we will, because again we were careful about these super polynomial drop-offs, we can separate the signal of detectors from within the region from detectors placed outside. Okay. When Wallace proposes his notion, he says that the approach actually is quite similar to what is happening in Haag-Euler scattering theory. So why not make this precise now? To compare the two notions, we have to sort of like bring them on equal grounds, and therefore we sort of consider fields that satisfy the Weigmann axioms, and then for some space-time region O, we consider the local polynomial field algebra, which basically is all the field operators local to that region, combinations of them. And such a Q is local if these functions that sort of designate the support for where we take the field operators from, if they have support within that region O. And let's call that a super W to sort of remind us that this is now something different. A's are not C star algebras, for example, anymore, only star algebras. We can also define almost local operators in this setting by having these functions not bounded support, but being from the Schwartz space, meaning that the functions themselves and all the derivatives decay super polynomially. All right, and then we can just take our detector or define our detector algebra in this setting as the almost local operators such that they are positive and annihilate the vacuum. Okay, now we can formulate both notions of localization within the same setting. So we can look at effectively localized. We call a state effectively localized if the difference of expectation values with vacuum expectation values drops off faster than Lie polynomial for operators from our Weigmann local algebras. can also say what it means to be almost localized, namely that simply the expectation values fall off faster than any polynomial for the observables taken from our detector algebra. What's the difference between those two definitions? Well, we have this term of comparing to the vacuum expectation values in the effective localization case. We could just add that here because that term is 0, because we assume that our almost local operators annihilate the vacuum. And that leaves us with the difference of, for effective localization, we take the operators to be from the strictly local algebras, and for almost localization, we take almost local operators that annihilate the vacuum. So the difference of how we go around the Reich-Leader theorem boils down to which observables we deem relevant for judging a state being localized in some region. So here again, the difference between effective and almost localization is which operators we think capture the relevant properties of a state to be localized in some region. For effective localization, we use strictly local algebras. For almost localization, we use our designated detector algebra that is based on almost local operators that are vacuum annihilating. So we might actually see a pattern and be tempted to generalize that and say, well, looks like we can sort of define a notion of operational localization, for which we have to choose two things. We first choose which operators do we want to test the state with, and then sort of a function that characterizes the fall-off of expectation values. In all of our examples, that has been super polynomially, but one could think of other requirements, depending on what you want. And then we say, well, a state is operationally localized in a region if, for the given and chosen notion of detectors and fall-off rate, we have that the difference between the expectation value in that state and the vacuum expectation values falls off with the distance of where we test this relative to the localization region. So we test all the state in all of space, and the farther away from our localization region that we test the state in, the smaller the difference to the vacuum expectation values should be for our chosen class of observables. And, well, again, the choice of the fall-off is always super polynomially, and for effective localization we look at strictly local operators, and for almost localization we look at the almost local positive vacuum annihilating operators. Turns out there are further options. There are some generalizations that I won't go into today that generalize this setting based on the notion of almost local operators and show that we can still have many of these notions in cases where the theory does not have a mass gap, which is the case for theories of, for example, charged particles. So any theory where we have a massless boson, we have problems constructing a Hilbert space, the Fock space, the one particle Hilbert space, because physically speaking, if we look at a charged particle emerging from some scattering event, it's always surrounded by what is called soft photons, photons of arbitrarily small energy. But that shouldn't be of our concern today, but it shows that this notion of operational localization is not idle. There are choices, and one can imagine that there's other choices even than that, that base their notion of localization on this principle. Okay, is this local enough? So can we having set out this notion of sort of approximate localization, can we convince ourselves that these things now make sense? Well, the answer depends a bit on how you read quantum field theory. There's, again, for the lack of better words, what I will call sort of two readings, the realist reading and the operationalist reading. The realist reading is we take the expectation values of operators localized somewhere in space-time to actually give us information about the excitation of the field in that region. So they actually denote properties of the system. Whereas sort of at the other end of the spectrum, there's the operationalist reading, where we would say something like, those observables represent operations or measurements in that region, and the expectation values give us statistical information about the measurement outcomes. That's sort of two ends of the spectrum. There's many nuances, and none of the mentioned people probably will be happy with me characterizing their view like that, but sort of just setting up the spectrum. So on the realist reading, as I said, we take the excitations, or we take the expectation values to actually denote excitations of the field. So if we have an operationally localized, regardless of which notion, localized state, then there will be genuine excitations of the system outside that localization region, space-like separated. That's of course a bit annoying if we want to take that state as being localized. So we sort of have to argue a bit, and I'll just use Wallace's argument here, who basically says, well, we need to include the measurement devices in our model of the system. So we shouldn't sort of pretend like the operationalist does that we can just extract the measurement outcome somehow without actually thinking about how the measurement device is entangled with the system or something. So basically, the idea is, well, detectors are made out of the non-local particles themselves. So they can't be any more localized than the actual particles. So what that boils down to is that the worries of the tails of localization basically only arise in highly idealized situations where we have an isolated system and we sort of talk about how that isolated system has these infinite tails in terms of its localizations. Whereas in reality, if I look at the system in my lab, that's an entangled mess. There's no exactly localized objects and no truly isolated subsystem. So the approximately localized states are themselves an idealization of reality, so we shouldn't worry too much about them not describing strictly localized systems. On the operationalist reading, this sounds rather different. As I said, the expectation values sort of represent statistical behavior of measurement devices. And there, if we sort of follow what Haag would say to that, well, real-world detectors also have a finite accuracy. And we know that almost local operators can be approximated by local ones to any given accuracy. So if we choose as that accuracy, the accuracy of our actual real-world detector, we can model it by a strictly local operator as well as with a almost local operator. So in the end, it doesn't really matter, because in the algebra of observables, if we take an epsilon wall, there will be so many different observables that can all model the behavior of our detector to the same degree, given that our detector has a given accuracy. So the difference between modeling a real-world particle detector with a local or an almost local operator is irrelevant for that, for describing the statistical behavior. And in fact, there's no one-to-one correspondence between measurement devices and observables anyways. If I give you a measurement device and ask you, write down the observable, that won't happen. And the other way around, if I give you an observable and ask you to build the detector that corresponds to exactly that observable, that also won't work. So we don't have this one-to-one correspondence anyways. So that's like almost a verbatim Haag. We cannot and we do not need to know whether real-world measurement devices now are modeled by local or almost local observables. So as long as the unsharpness in localization is only up to the real-world accuracy of our detection devices, we can't model the difference anyways. Okay. Whether you're convinced by the realist or the operationalist story, or by neither, that would be a bit sad. I think on both of those readings, one can justify that these notions of localizations actually suffice somehow. Because I'm biased and have a slight preference for the operationalist reading, and I think we can give a little reason for that, because the schema of operational localization shows that there is a choice involved in either way how you model localization of a state. You have to choose which operators you take to describe or to extract the relevant properties of the state for localization. And that's quite okay on the operational reading. Choices correspond to different real-world detectors or to different thoughts about those detectors, or how we think about those detectors. However, it's a bit less clear on the realist reading how one could defend that we only test the state with a subset of operators for being truly localized. I'm not saying it's impossible. I don't think much hinges on that. It's just sort of like why I think there should be a slight preference for the operational reading. Okay. So somehow we now arrived at a notion of localization for states. We can say a state is localized in this region of space-time. How are we to describe particle states? In particular, we want to describe non-interacting particles, free particles, so they will be far separated so that they don't interact with each other. And well, the natural idea is, well, we want a state to have n regions where it's localized in. And this is exactly the idea behind this definition by Haag, who defines a state to be called at most n-fold localized if we test the state with n+1 detectors, far separated from space-time, and that cannot produce a response of all the detectors simultaneously. So if it's n-fold localized, then any n+1 fold, Haag calls those detector arrangements, cannot produce a signal. Of course, if it's only n detectors, we would expect the state to be to produce a signal in that. If such a state that is at most n-fold localized cannot be written as a mixed state involving an at most n-1 fold localized state, then we shall call the state exactly n-fold localized. That is basically to say we don't want a state to be n-fold localized because it's a mixture between a state that is n-1 fold localized and an n-fold localized state. Okay, so we're placing detectors all over space, check whether they trigger, and therefore get a notion of how many particles or how many localization centers this state has, or how many localization regions. And so Haag proposes we should call a particle state, or a state, an n-particle state of n freely non-interacting particles if it is constantly n-fold localized. So we at all times have n localization centers. Some notes on that. We do somehow ignore the information about where those localization centers are. We just say, okay, there shall be n. It will turn out in the bonus discussion on interactions that we can actually say more, but in that definition of n-fold localization, we mainly care about there's n separate localization regions. This only works with almost local operators. So we need to choose for our operational localization, we need to choose something that builds upon almost local operators. Because for strictly local operators, remember we had to always compare them to their vacuum expectation values. And the problem now is if they have non-zero vacuum expectation values, we cannot separate those non-zero vacuum expectation values from genuine responses to multi-particle states. So this really needs that the observables we use are zero in the vacuum. So one might say, on this account of an n-particle state, effective localization does not generalize to multi-particle states. We need the almost localized operators. Okay, we're very good in time. So regarding the localization, this is the story I wanted to tell you. We have seen that there's basically the Risch-Leader theorem can be formulated as a sort of dilemma between two different properties we both want to have, and there's sort of two different responses to that, and they lead to effective and almost localization. I have proposed a notion of operational localization that sort of looks at the overarching idea that basically is state looks like the vacuum outside of the bounded region if we test it with this choice of detector observables. And we've then also seen that the difference between effective and almost localization is mainly this choice of operators that we take to test the state. And if we want to generalize that to multi-particle states, we have to choose something that is based on almost local operators. Okay, now sort of a little outlook where I'll give less details about how we can use this notion of particle states as being as containing localization centers in the context of interactions to see how the free particles sort of emerge from that. Well, here's a picture of the LHC in Geneva, and a typical particle experiment there will look something like we prepare a state of incoming particles. We accelerate protons having almost opposite momenta at the collision points. We then let them collide or interact almost head-on, and we've placed very expensive machines around this collision center to measure the state of outgoing particles. And the idea now is to sort of model this overall shape of these high energy physics experiments by recognizing, well, the free particles certainly occur only long before and long after the collision. Long before we sort of, it's very idealized but simplified, we prepare the two protons and there's still two protons non-interacting until we let them collide. And long after the collision, when the products of the collision separate and hit our particle detectors, then again they're sort of free particles. Mathematically, this is modeled with the use of scattering theory. The idea is, well, we just want to model such an experiment as a transition from the prepared ingoing states to the detected outgoing states. And so we want to write it very simply as we have an incoming state of n particles with these momenta and other degrees of freedom maybe. We have this state of outgoing particles, and we just want to see how does the incoming state transition to the outgoing state with the help of the scattering matrix. Well, there is a problem because Haag's theorem prohibits sort of switching interactions on and off. Basically, Haag's theorem implies that if we want to have this incoming state and this outgoing state to be free states, that all the states in between, if evolution is unitary, will also have to be free. So we'll never get interactions. That's a bit annoying. And so the solution mathematically is that we model the in and out states as limit states. So we say, well, it's not only a long time before and after the collision, but if we actually say it's an infinite time before and after the collision, then we can sort of avoid having the states directly connected to each other. And if we only talk about them in terms of limit states, we don't get into trouble with Haag's theorem. This is very simplified, but I hope not too simple. It's to be false. And in Haag-realist scattering theory, what one actually does is one creates a series of states that, for the asymptotic limits t to plus or minus infinity, converge to a state that looks like a multi-particle state. The idea is, and why we don't get into trouble with Haag's theorem, these states here are states of the interacting theory, and this state is also still a state constructed from the interacting theory. It just behaves like a multi-particle state, or it looks like a multi-particle state. Can we somehow apply our idea of operational localization and the multi-particle states arising from that to this situation? Oh well, actually, before we do that, we briefly have to discuss what usually is done to deal with that situation. So we've just seen that scattering theory can show us that states converge to free states. So the usual thing what one does is, okay, we only need a notion of particles for free theories. Scattering theory tells us at the asymptotic times it will be a free theory, so why bother with anything else if we have free theories and have actually quite nice conceptions of particles there. In fact, one can, Fraser argued that interacting systems actually cannot be interpreted in terms of particles if we take if we take what we mean by particle to have a Fock space structure that's compatible with the asymptotic time Fock space structure. Jonathan Bain then says, well, we should actually take scattering theory a bit more seriously and not just start with free theories, but actually take particle states to be those states that asymptotically look like free states. This might sort of be a very small difference, but conceptually it's quite an important difference, I think. Whether I say, okay, I'll start with free theories, scattering theory somehow manages to justify this, or whether I say, no, I'm taking those asymptotic states and try to see those as particle states. Now we ask whether we can apply our idea of particle states to this situation, and it turns out that this criterion of n-fold localized states can be applied to these asymptotic particle states constructed in Haag-realist scattering theory. So the asymptotic states in that scenario are n-fold localized states, the way we sort of set the thing up. In fact, we can extend this to finite times. We can call a state a particle state if it is n-fold localized for all times earlier and later than a given threshold. If the state is, with the appropriate notion of localization, n-fold localized at these times, we can call that a particle state. And we can even get more. If we construct those limits, this family of states and the limit state, as it is done in Haag scattering theory under certain assumptions, we can actually show that the response of these states for large T to an arrangement of M detectors, as we had it before, as we defined our notion of n-fold localized states, then this expectation value behaves for large T like the product of taking these detector observables and applying them directly to the single particle states. This is for m being smaller or equal to n, so this is just normalization stuff. And if we look very closely, this is proved for if we send those arrangements of detectors along the sort of classical trajectories of the particles. So if we have a particle that has a momentum with certain velocity, as I'm saying, there's a few asterisks attached to this, we actually get that the response of that state behaves like separating localization regions. So, using operational localization with almost local operators, we can describe single particle states as approximately localized in bounded regions. We can describe multi-particle states as states that have n distinct localization regions. And we can actually trace those localization centers throughout the time limit in scattering theory. So what we get is a sort of operational particle picture. We can say particles are what the particle detectors, as modeled by our observables, detect. And we sort of have as a big conclusion, this all depends on the choice of detectors. As I said, there's a generalization which is proposed by Buchholz and others to theories that don't contain a mass gap, where there is actually no asymptotic state, so that the limit does not exist in the strong sense. But we can still apply the n-fold localized criterion. We can still call those states particle states on this notion of particles, even if we don't have an actual Fock space. That's actually all it I wanted to tell you. So there's anyways only the conclusion left. So the goal was we wanted a particle phenomenology without having to assume a particle ontology. We wanted something that can model localized states, at least approximately, model states that consist of several non-interacting particles, and sort of show how these emerge from an interacting theory. The proposed notion of operational particles ticks all the three boxes. We have something that models localized state as something that responds to our particle detectors only within a given region and not outside. We can extend that to n-fold localized states, to states that contain n localization centers, and we can use that to see how the states that emerge from scattering theory, Haag scattering theory in that in particular case, we can show how these free particles in this sense emerge. Thanks very much.